Hello, everyone. My name is Magdalena Gargas, and I'm a solutions architect working for AWS in Switzerland. Maybe before we start, let me know if you can hear me. Can you hear me? Super good. Thanks a lot. So today I'm joined by my friend and colleague Nat Nordanus, staff software engineer at Nextwing. Welcome to this session on best practices for data analytics and generative AI on AWS. Since you are here, I already assume that you have got some knowledge about AWS services, so you probably tried few of them, and that you are familiar with the concepts like data lake or analytics pipeline. So I won't be covering those concepts in the details. Instead, in our session, I will be focusing about data analytics for generative AI applications, and with the help of a demo reference architecture, we will see how data pipeline can enable generative AI application. We will also share cost and performance influencing best practices, and Nat will take you for the journey, so generative and analytics journey of Nextwing. Let's get started. So generative AI is a new technology, arguably experimental for many of the companies. However, I doubted that there is anyone in this room that either heard about it or tried it in some shape or form. And similarly, we see very creative ways how AWS customers are building their generative AI application. So just to mention a few use cases, those are chatbot applications. They are using generative AI to summarize the long-form documents, so the talks documents, and they are also using generative AI to generate a code. Similarly, they're using few architecture patterns to build their generative AI applications. So depending on a pattern or approach used, their grounding capability, which is capability to successfully use information, will differ from the purpose-driven to the generic, and similarly will influence their adoption experience. First pattern is to train your own model. So this is really custom-made solutions. So on a vast amount of domain-specific data, we are training model to perform a specific task. A good example here might be a Bloomberg GPT LLM, which is trained on financial data to perform financial tasks. Fine-tune a pre-trained model is approach when you take a large language model and you train it further on a smaller set of labeled data. And finally, the most generic approach is in-context learning. This is approach when we do not alter the model, we do not change its parameters, we do not train it further, but instead we are providing to the model some additional context. And this context can be either situational or semantical, or both. A good example of the in-context learning pattern is prompt engineering or retrieval augmented generation, so-called RAG use cases. So let's look now at the in-context learning pattern. So first, the user submits the prompt to the generative AI applications, and a large language model extracts the keywords from this prompt, and based on those keywords, we are getting relevant information from the company data sources. So it can be data warehouse, it can be data lake, those can be also vector databases. With those relevant informations, then we are building those relevant information we are then sending to the large language model and building the generative AI response. So part of the information in the company is stored in the databases, in the data lakes and data warehouses. But also huge amount of information is stored in the documents, in the images. Those kind of informations can be also used by large language models using vector databases. So now let's look what are vector databases and what are vector embeddings. So the vector embeddings allow us to create the numerical representations of the data, keeping their meaning and relationship. So to create the vector embeddings, first we ingest the data, then we split the data into manageable chunks, and create the numerical representation of this data that is later used by the vector database to store the relevant informations. From the vector database, generative AI application can easily extract the relevant informations. So we've seen a workflow. Now let's look how it looks in real time. So this is an example of generative AI applications that helps to build the promotion documents for AWS employees. So AWS is a very data-driven company. Therefore, anytime any employee wants to be promoted, it needs to provide the document summarizing their own achievements. To do this, so in the question prompt, we are passing some situational context, like who the employee is, what is his current role, what is his desired role. And we also passing some information about the contributions made by the employee. In the response, we are using this data to retrieve additional information from the company data warehouse about this employee contributions. And we are also use semantical context like example promo docs, level matrix, leadership principles to provide the relevant form for large language model to answer. So we've seen how it works in real time. Now let's look what AWS services are used underneath it. So you are already familiar with the generative AI workflow for the in-context learning. Now we'll be using same workflow, but this time referencing AWS services. So first, the user submits the query to the generative AI application. Then we are retrieving relevant conversational context from the DynamoDB. And with this context, we are building queries to the company data warehouses. Once we have the data from the company data warehouses, we can also extract the semantical context from the Amazon OpenSearch serverless service, where we are storing those example promo docs, leadership principles, and level matrix. This information then is passed to the large language model that later formulates the response. And this response is again stored in a conversation history in DynamoDB and returned to the user. So this is very typical workflow for generative AI. Now let's look at the data pipeline that powers this workflow. So you might think, so let us think, for example, so let us think about the example where we want to give the customer really relevant data. So, for example, some chatbot applications might need to have the access to the real-time data. Think about booking planes, right? So when you book a plane, you need to have access to the price, and you need to have access to the current booking stage for the plane. This information is typically not stored in a company data warehouse. Therefore, we need to get it from the other data sources. So those informations can be streamed into our application using Amazon MSK or other AWS services for streaming. So we're streaming this real-time data from various data sources into our service, and from these data sources, we are retrieving relevant information for the generative AI application and storing it in the conversational state history in DynamoDB. Also, part of this data, we might want to save on S3 for further processing. So now let's look how data should be laid down on S3 to optimize it for data analytics. So when we are talking about the analytic workloads, we typically deal with the large volumes, but we select only subset of columns and apply filters. To optimize the performance, we want to reduce the data to also optimize the I/O. So the first thing we can do is to partition our data using the most common filters. We can also use columnar formats like Parquet or ORC. Oh, sorry. Sorry. Remember about using splittable compression formats like ISO or Snappy. And remember about storing your data files in the files that have got between 128 and 512 megabytes. Those best practices apply also not only for storing data, but also for running analytical queries on data. So we've seen the data ingestion. We've seen that we can store the data on S3. Now we want to integrate it, clean it, and transform it using business rules. Integrate it in a way that they are available for consumption. So we can do this using our processing data services, Amazon EMR and AWS Glue. So for data processing, Amazon EMR and AWS Glue. AWS Glue is a serverless managed service for data integration. It allows you to integrate various data sources with the destinations. And example data sources might be here the AWS services or other data sources. And you can also use connectors from AWS Marketplace. Open source engines for data processing, the data catalog for data quality, and you can also use data catalog to catalog your data that is stored on S3 and metadata of the DynamoDB. For job authoring serving different personas, you can use a visual drag and drop editor for low-code, no-code user, and interactive notebook sessions for developers. AWS Glue supports monitoring and scheduling, batch and event-driven. When we are creating jobs, typically the jobs need to serve different personas and different use cases. Therefore, we have got different engines on AWS Glue. One engine here is a Python shell that helps you build the single node workloads. And another engine is Ray and Apache Spark that helps you build distributed workloads. When you create the Apache Spark job, you can choose the right worker type for your SLA and choose between the standard and flexible execution. Glue flexible execution helps you optimize the cost. So Glue will provide you with the spared capacity at the reduced cost, but remember to use it for non-time sensitive workloads. So to summarize, let's look at a few best practices, how we can configure Glue jobs. So first of all, choose the right worker type for your workloads. Use the latest version engine for Glue. Enable auto-scaling to allow Glue track your demand. And set timeout. So the default timeout is 48 hours. For your workloads, you might need less. For incremental processing, enable job bookmarking, which also supports checkpoints. And for Spark application, you can use push-down predicates. And remember about optimizing your JSA, so reducing your JSA before running joins to reduce I/O. But when you have got really big workloads, you want to look into Amazon EMR. Amazon EMR is a managed service for big data processing. And it supports open source service and supports open source frameworks like Spark, Hive, Presto, HBase, and more. For each of those open source frameworks, the latest version is picked by Amazon EMR, not past 60 days after it's released to the open source. And there are multiple ways how you can set up Amazon EMR on AWS. So first deployment option is to use Amazon EMR on EC2, which allows you to choose the instance type and choose the amount of instances that will be running in this workload. It also supports a wide variety of the open source frameworks. If you are already using Amazon EKS, so Amazon Elastic Kubernetes Service, and you are already running Spark applications, you might want to use Amazon EMR on Amazon EKS. To completely simplify your experience, use Amazon EMR serverless. And if you want to keep your Amazon EMR close to your on-prem, you can run it on AWS Outposts. Now, let's look at the architecture of the Amazon EMR. So we have got the leader node, a core node with HDFS, meaning storage, and the task node, meaning compute. And there are two ways how you can deploy Amazon EMR on EC2. First way is to use unified instance group. It's a really good choice when you're just starting with Amazon EMR or if your workloads are very simple. With unified instance group, you can select one instance, so you can select either on-demand or spot, and use this to provision your cluster. For more complicated workloads, you want to use instance fleet. With instance fleet, you will have got one instance fleet and one task fleet, and for each of them, you can use mix of on-demand and spot instances. You can use allocation strategy that allows you to choose the cheapest on-demand instance and the cheapest spot instance, but with the highest capacity. So depending on your needs, if your workloads are really simple, use unified instance group. If your workloads are more complicated and you want really to get the performance from Amazon EMR, use instance fleet. A good option also to save costs is to use EMR with the spot instances, especially when you are running Spark workloads, because Spark handles well these spot interruptions. Summarizing, choose the right worker type based on your SLAs. Use Graviton 2 instances to provides best price performance. Consider using spot instances. And always monitor and instrument your workloads. So in this part of the presentation, we've seen the generative AI workflow. We've seen how data pipeline enables this generative AI workflow. And I also shared few best practices for building data lake and processing data. Now, over to Nat, who will show you how Nextthing build their generative AI applications and the data pipeline.
Thanks, Magda. Good morning. I work for a company called Nextthing, and our customers are IT departments of large enterprises with a focus on end-user computing. We offer them a SaaS product called Nextthing Infinity, which is a platform for digital workplace, observability, and automation. This includes modules for real-time alerting and diagnostics of IT issues, as well as automated remediation. We have tools for a variety of personas, from the IT help desk to application owners or workplace architects, among others. And of course, in all areas, we're investing heavily in AI. For a long time, this meant using conventional AI to generate targeted insights for optimization or troubleshooting. But now we also have a Gen AI-powered virtual assistant that helps users generate content or query their data with our bespoke query language called NQL. The digital workplace is complicated. There are hundreds of factors that can impact the experience of an employee with IT at work, from the specifics of their device through to applications running in the cloud. So we monitor all of them from the perspective of the end user. This means that each monitored device sends us a few hundred metrics every few minutes to provide a comprehensive picture of what's going on for that device. We have customers spread over many regions and different industries, including some you've probably heard of. And we partner with most major IT service providers. So with 18 million installed endpoints, this means that we process trillions of events per day. That's a lot of data. So with that, I'm going to tell you a bit about how we get value from this data using a data lake built on AWS. But first, I want to explain how this data lake fits into our broader architecture of our product. So Nexthink Infinity runs on a purpose-built platform in the cloud to serve near real-time analytics, leveraging ClickHouse and Kafka on AWS. It's implemented as a multi-tenant cellular architecture with cells distributed across 10 different AWS regions in order to be closer to customers. Some of the data that we process for our customers is quite sensitive, including PII. So access to underlying data stores is highly restricted. Meanwhile, our data scientists, who work on developing new data-driven features for our product, need to work with data directly, whilst maintaining strong protections for PII. And to discover trends and patterns across all our customers at once, data needs to be centralized in a single region. And we need to use infrastructure that's optimized for cost-effective offline processing, which tends to imply ephemeral or serverless infrastructure components. So this is why we decided to implement a separate data lake environment alongside our existing product platform. So we started by creating a separate set of AWS accounts. So we have a dev, staging, and prod account for the data lake alongside the corresponding accounts for the product platform. This is a best practice to optimize infrastructure deployment and data governance concerns. Then we implemented a new microservice in our existing Kubernetes cluster in Amazon EKS that extracts existing or consumes existing data sources in Kafka running on Amazon MSK. And this microservice is responsible for implementing anonymization policies on the data before writing it to a landing zone bucket in our data lake. So PII never leaves the source system. Now I'm going to call out a few more implementation details that are important for this process. So we use the Avro file format for files written to S3, which offers efficient binary encoding and data compression. It also has an explicitly typed schema, which is compatible with the Glue data catalog, making this data easier to work with later in the data lake. Most importantly, it's a row-oriented format, which means that we can continuously append rows to these files and use the S3's multi-part upload API to stream data into optimally sized files in S3 without having to buffer much data on the extraction microservice. Now, we have the source system is distributed across 10 different regions. And even with compression, the data that we move along this pipeline is on the order of about 5 terabytes per day. So, as you probably know, AWS charges for egress out over the internet, including between AWS services in different regions. So to avoid this, we create a landing zone bucket in every region, and we configure an AWS private link on the VPC hosting the extraction microservice to allow direct connectivity to S3 in that region. Now, deriving value from data, from large data volumes, can be quite challenging. Specifically, the data that we ingest into the data lake is very detailed and low level, which is valuable, but makes this data difficult to analyze. So we needed to put in place some pre-processing pipelines to make the data more usable. This includes some cleaning and aggregation of the data and pre-joining of certain fact and dimension tables that would be too large to query, to join at query time. To orchestrate these data pipelines, we use AWS step functions. What we like about step functions is that it's fully serverless and integrates natively with many other AWS services. Now, the first thing we do with any newly ingested data in the data lake, as part of one of these workflows, is run a Glue crawler over it. And this creates the required metadata in the Glue data catalog, so that all the data in our data lake is tracked and modeled as part of that catalog. When it comes to processing large data sets, we use Apache Spark on EMR. EMR takes most of the complexity out of managing Spark clusters. So for instance, we're able to make all of our clusters ephemeral by setting them up and tearing them down as part of a workflow. And we use EMR instance fleets to automatically right-size our clusters as the workflow progresses, and using mostly spot instances. This is quite complex to tune at first, but does save us a lot in EC2 costs. And for any jobs that don't require distributed data processing as part of a workflow, we use Lambda functions. Now, along with the along with the reduced size of data that we get from the aggregation, we also get some improved compression by writing data back into a different location in S3 in Parquet format. Parquet also has the advantage of, since it's a column-oriented format, of being much more efficient to query. And some of our workflows produce trained models, which we then also reintegrate back into our product environment to power user-facing features. Some of our workflows also process up to 100 billion events over a dozen stages in a single run. And this inevitably means that there's a certain failure rate of these workflows. So to make sure that we're notified of this, we leverage the native integration between step functions and EventBridge, such that whenever a step function enters a failure state, this triggers EventBridge to trigger a Lambda function that sends us a message on a Teams channel for the team to react to. Our data lake serves a variety of use cases, including reporting and analytics based on the centralized preprocessed data in S3. And data workspaces are what we call our solution to the problem of how to provide internal users with well-scoped access to data and the tools that they need to work with it. Each data workspace consists of the following components. Firstly, there's an isolated Glue database that contains only the tables that these users require access to, and which they can also create their own tables. Note that if tables are duplicated across databases, only the metadata is duplicated. All instances of a table in different workspaces will reference the same underlying data in S3. Then we have a dedicated Athena workgroup that allows the users in the workspace to query their Glue tables and to share queries with each other. It also allows us to easily track costs of each workspace in terms of the costs of those queries in Athena independently. And we provide users with a dedicated S3 sandbox bucket to save their query results and any other data that they create. Users access a workspace by assuming an IAM role that they're specifically given permission to that provides access to all the resources in this workspace. And we use lake formation to provide fine-grained access control on data by assigning LF tags to the columns that are specifically allowed for users to access in this workspace. Now, generally, Athena SQL is our preferred way to provide users with access to data. But for some more advanced users that know Python and want something a little bit more powerful, we also allow them to use Athena serverless PySpark notebooks. And for less technical users, we provide Amazon QuickSight business intelligence dashboards, which are also underneath powered by Athena. And all of this data workspace pattern is implemented as a Terraform module, which greatly simplifies the process of creating or modifying existing workspaces. So now you know a bit about how we approach analytics at scale. Let's shift focus to how we're building on this foundation with generative AI. For a product team, the goal when working with cross-customer data is to leverage the data that we collect and process for all our customers to derive knowledge and intelligence that we can then reintegrate into our product to better serve each individual customer. In our data lake, we have a unique and powerful data set about end-user computing and devices and applications. When we think about deriving knowledge from data, this can mean computing benchmarks to allow customers to compare themselves on key metrics with the average of their peers, or tracking usage trends to inform our customers' IT strategies. We can also supplement this knowledge with machine learning and heuristics to deliver more intelligent product features. This can mean, for example, we can shortcut the IT troubleshooting process by proactively informing our customers when their users may be impacted by known issues and recommending remediations based on what we've observed from other customers. As I mentioned before, our product also features a Gen AI virtual assistant, and it's worth noting that having more well-organized and well-structured knowledge available is useful for the assistant to be able to more often provide users with exactly the insights that they need. Therefore, an important part of our strategy is to build an expansive knowledge base about the tens of thousands of desktop applications, web applications, and hardware configurations that are commonly used in industry. A lot of this knowledge can be derived from the data we collect, but some things are missing, such as knowledge about specific applications and what they're used for. So, as a new feature in this space, we wanted to be able to categorize applications based on what they're used for, and annotate applications in our product with the category and subcategory that is most relevant to what those applications are. So this will enable our users to easily answer new kinds of questions with our product. Questions like, what communication tools are used in my company today? Or which employees or which departments use tools for data analysis? And this is where we saw an opportunity to leverage large language models. Models like Anthropic Claude have been trained on sample text on virtually every topic on the web. This includes documentation and marketing materials about software applications from vendors' websites. So we set out to bootstrap a knowledge base of application categories using an LLM as a source of information. So how does this work? Now I'm going to walk you through the different Gen AI tasks that we composed to solve this problem. The first step was just to generate a description of the entities that we want to categorize. It starts by asking a simple question. The prompts that we use were a little bit more involved than the example on the slide, but this demonstrates well already the principle of extracting foundational knowledge whilst avoiding hallucinations. The next step was to use the LLM again to generate vector embeddings from the descriptions in step 1, which represent the text as a point in a high-dimensional space, such that different application descriptions with similar topics will naturally cluster together. We then ran these embeddings through an agglomerative clustering algorithm and created about 20 groups of applications with similar descriptions. The next task is to generate a summary for each group. So we fed the LLM a sample of application descriptions, applications and their descriptions from each group, and asked it to provide a summary of that group and a category label. And with this, we had the first iteration of our application categories based entirely on knowledge from an LLM. At this point, we also included some manual human supervision to have some experts tweak the categories and their descriptions. The final step is to assign each category, each application to the best category, which is essentially a classification task. To classify an application, we first give the LLM the details of the application, including its name and description. Then we give it the names and descriptions of all the categories that it might belong to. And we ask it which category, if any, is most applicable to this application. And finally, we're able to generate another level of subcategories by repeating parts of this process on the applications within a single category in isolation. So now you have an idea of how our solution works. Here are some things that we learned along the way. Now you might imagine that this process could be a little bit simpler. Maybe we could just ask the LLM to categorize an application in one go. It has all the knowledge after all. And this actually sort of works. But one insight we had is that similar to some other creative processes, you get much better results if you diverge before converging. And what I mean by this is that we first ask the LLM to output the knowledge that it has in the form of a description with a specific kind of structure, including certain details, and then explicitly use that knowledge in the classification step. Sending a whole prompt for each individual application that we wanted to process would be quite inefficient in terms of token usage. So a common technique is to batch multiple items into a single prompt. Batching too many items together, however, can hurt accuracy. So with a bit of experimentation, we found that 20 items per prompt worked well. Large language models are stochastic, which means that the results in the classification task can vary a little bit randomly from one trial to another, and you don't always get the best result on the first trial. So we implemented a repeated sampling strategy, whereby we asked the LLM to categorize each application 5 times, and then we take the consistency across trials as a measure of confidence. We also shuffle the batches between each trial, such as to remove any bias that might come from the batch composition. And often, when working with LLMs, one easy way to improve performance is simply to upgrade to the latest model. So for example, when Claude 3.5 came out on Bedrock, and we upgraded from Claude 3, we observed immediately a 5% improvement on some of our evaluations. Now, building a knowledge base like this is a process that, well, in the previous slide I made it sound quite linear, but actually a lot of experimentation and iteration and learning along the way was required to get a good result. So we needed a strategy for how to incorporate all of these small changes into the knowledge base as we went, including human feedback, both in the form of a golden data set for evaluation purposes and as a way to improve the quality in some areas. I'm going to explain a bit about how we composed that strategy, but first I think it's useful to look at how we integrated this process into our existing infrastructure. So when it comes to calling LLMs, of course, Amazon Bedrock is our preferred, how we do that, and our preferred model so far is Claude Sonnet from Anthropic. We already had a regularly scheduled workflow that analyzes applications, so we extended it to call Bedrock via a Lambda function using a popular Python library called LangChain, and to maintain the knowledge base of application categories, which we implemented as a table in DynamoDB. Once the knowledge base is up to date, then we generate several data sets from it and publish them into the product environment to power customer-facing features, including our Next Thing Assist, our virtual assistant. Well, I'd love to say more about how how this assistant works and the RAG and content generation features, but that's a topic for another presentation. These processes, oops, got ahead of myself there. So this is the workflow that automates keeping our knowledge base up to date. But there are some processes that we also need to incorporate to make iterative improvements, such as if we want to try a new model or adjust a prompt or add or remove a category or something like this. And we certainly don't want to have to generate the whole knowledge base from scratch every time. So these processes require a more manual approach, which is better orchestrated from a Jupyter notebook. When we make incremental changes to the process, we need to be able to evaluate the impact of the change against a carefully targeted subset of the knowledge base. For example, to see which categories get applied differently or measure accuracy against our manually labeled golden data. And when we apply these changes, we only want to update entries in the knowledge base where we expect to see an improvement, such as those with low confidence that already belong to similar categories. Now, to implement the database, to the knowledge base, we could have used almost anything, but I'll tell you why DynamoDB was an ideal fit. As a serverless offering, it couldn't be easier to operate, and at this scale, it's very cost-effective. Also, having a flexible NoSQL schema makes it easy to maintain and query rich metadata, which is important when sampling data for evaluating changes. We're also able to maintain an auditable or complete full history of each item in the knowledge base by having the application identifier as the partition key and a version timestamp as the sort key. So this means that we can always query for the latest version of a item in the knowledge base, which should be the best, but if for whatever reason we want to roll back to a previous version, that's still available. So all updates to the knowledge base are non-destructive. Also, working with Bedrock to process a large amount of data, and inevitably we encountered quite a few issues with throttling and rate limits. Now, if this were an application with persistently high load, of course the solution would be to purchase provision throughput from AWS. But since this was mostly a one-off kind of process for processing large amounts of data, we handled this by reducing the concurrency of the Lambda function, processing and committing small idempotent matches for the knowledge base, and of course a good retry strategy. So finally, let's recap what we've covered today about NextThink's experience. I explained how we implemented a data lake and data processing infrastructure alongside our existing product platform, how we leveraged serverless and managed offerings such as step functions, Glue, EMR, and Athena and Lambda to automate dozens of data pipelines across 10 different regions whilst managing infrastructure and operational costs. I showed you how we managed workspaces for different kinds of internal users to access and analyze data. Then I shared something about our cross-customer data strategy by building knowledge and intelligence on top of our data to enhance our product offering. And I explained the different generative AI tasks where that were involved in solving the problem of categorizing applications. And also how we extended our existing architecture to handle the challenges of iterating on this solution and automating it in production using Lambda, Bedrock, and DynamoDB. I'd be happy to talk about any of this afterwards in person, and you can also come and say hi at our NextThink booth. I think it's S2 in the foyer. And now I'm going to hand it back to Magda to wrap up.
Thanks, Nat. Lots of learning and a great story. Thanks a lot. So just to... Yeah, good stuff, Nat. Thanks. So 2 more slides. Just to summarize the whole presentation. With the help of the demo reference architecture and with the help of Nat example, we've seen that with generative AI, we really bring some data sources to the mainstream. An example here might be a vector databases, which aren't new concept per se, but really with the generative AI applications, they are commonly used. Similarly with unstructured data. So in the past, we've seen explosion of the unstructured data, but it was very hard to get the insights from this data. With generative AI, with large language models, now it's easy. Nat also shared some best practices. How can you build the privacy and security around your data? And finally, the theme that was showing up through whole presentation is that the data quality is really differentiator for your generative AI workloads. So thanks a lot for this session. If you are interested in any topic that we covered, here there are some resources. Oh, sorry. Yeah. So thanks a lot for this session. If you have got any questions, we'll be here around. So please let us know. Ask the questions. Ask me. Ask Nat the questions. And if you like the session, we always say that the feedback is a gift. So please find our session in the app and give the feedback. Thanks a lot for today. That's it.